Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Welcome back. Today we are strapping in for quite a journey. We're diving into a universe that doesn't actually exist in the sky, but inside a supercomputer.
That's right. We're talking about the Flagship 2 Galaxy Mock simulation. It's genuinely the largest, most detailed synthetic simulation of the cosmos ever put together.
An unprecedented scientific achievement, really, and it's absolutely foundational for what's coming next in astronomy.
Absolutely. So our mission today is to unpack this thing, Flagship 2. If you're, say, prepping for a big meeting on where cosmology is headed, or maybe you just want to grasp how scientists are actually going to handle the insane amount of data coming our way,
then this is the place to be. This simulation, it's not just some cool tech demo.
No, not at all. It's the essential blueprint, the roadmap for discovery.
And the scale of this blueprint, that's what really jumps out first. When we say largest, we mean, well, utterly staggering numbers.
Yeah.
We're talking about a digital universe with 3.4 billion simulated galaxies inside it. Just try to wrap your head around that amount of information.
It's almost impossible. And scientists built this simulated reality very deliberately to get ready for, and then, ultimately interpret the flood of data that's coming from ESA's Euclid mission.
The European Space Agency's big eye in the sky.
Exactly. And what's really critical here, you see, is that this simulation does two key jobs. It serves two masters, if you like.
Okay.
On one hand, preparation. It lets the Euclid team build and, crucially, test their analysis methods, their software pipelines.
Right, ironing out the bugs before the real data hits.
Precisely. But on the other hand, there's a kind of prophecy aspect. Because the simulation is built on our current best understanding of the universe, the standard model of cosmology.
Yeah.
It creates this perfect theoretical prediction.
So it's like, here's what the universe should look like according to our theories.
Exactly. It builds the target that reality, the actual data from Euclid, has to either hit or miss.
And as we dig into the sources talking about this work, stuff from the Euclid Consortium, and especially these amazing algorithms from UZH professor Jochen Stadel and his team, we start to see the whole point is actually designed to find the flaws. They're actively looking for where reality might just shatter the theory. They call it searching for cracks in the standard model.
It's a really sophisticated strategy. We're going to explore how they built this computational colossus, why it's basically the only way forward when you're facing this data avalanche.
Right.
And maybe most excitingly, what kind of potential scientific revolution it could actually trigger.
Okay, let's unpack this journey then. Starting with just the mind-bending scale and the cleverness needed to build this digital cosmos in the first place. We really have to start with the architect, don't we? Behind this massive scale Flagship 2, you mentioned Jochen Stadel, the astrophysicist at UZH. He developed the algorithms that really underpin the whole simulation.
That's the key. Because when you're trying to model 3.4 billion objects, the complexity, it just explodes. It's not linear, it's exponential.
So it wasn't just about getting a bigger computer.
Not at all. It was about having the mathematical insight, the genius really, to handle the gravitational interactions between all those objects efficiently.
The famous n-body problem, right? Calculating how everything pulls on everything else.
Exactly. And that's the core challenge in any cosmology simulation. Billions, or in this case, trillions of particles.
Wow.
Previous simulations always had to compromise. Either you simulated a big volume with low detail or a small volume with high detail.
You couldn't have both.
Right. Stadel's work was about optimizing the calculation, finding clever ways to group particles and calculate forces so they could manage both scale and resolution. The raw computing power is kind of useless without the smart algorithms to distribute the work and calculate those dynamic interactions across huge cosmic distances effectively.
And the result of that optimization is just, wow, let's say that number again, 3.4 billion galaxies. That gives you the size of the simulated patch of universe.
And the volume.
But you pointed out the real complexity comes from the depth of the data for each one. What kind of details are we talking about for each galaxy?
Oh, it's incredibly detailed. We're talking high-resolution data designed to mimic what the real Euclid telescope will actually capture. Each of those 3.4 billion galaxies isn't just a point of light.
Right.
Each one has 400 modeled properties. 400.
400 properties per galaxy. Like, what?
Well, the basics you'd expect: brightness, its position in 3D space, its velocity, how fast it's moving, but then crucial details like its metallicity, how many heavy elements it has,
Okay.
its star formation history when its stars were born, and critically, for one of Euclid's main goals, its precise shape and orientation, its ellipticity.
Why is the shape, the ellipticity, so important that they'd spend all that computational effort modeling it 3.4 billion times?
Because that's the bedrock of the dark matter mapping effort. We'll get more into this, but basically, Euclid finds dark matter by looking for tiny distortions in the shapes of background galaxies caused by gravitational lenses.
Right, the lake it's bent by unseen mass.
Exactly. So if your synthetic universe, your simulation, doesn't have accurately modeled galaxy shapes to begin with, you can't properly train the software that's supposed to detect those lensing distortions in the real data.
So you wouldn't know if your software was working correctly?
Precisely. You couldn't accurately interpret the real observations. Those 400 properties are what tie the simulation directly to the specific physics and the specific measurements Euclid is designed to make.
Okay, and tracing back even further, before they even put the galaxies in, the underlying structure, the cosmic web, that came from an even bigger calculation, didn't it?
Oh yes. Before populating it with galaxies, the simulation first built the large-scale structure, the scaffolding of the universe, you could say, the dark matter halos and the filaments connecting them.
The cosmic web.
That's it. And that structure was built by tracking the gravitational interactions of, wait for it, 4 trillion particles.
4 trillion, Trillion.
4 trillion individual points, each representing a chunk of mass pulling on every other chunk over billions of years of simulated cosmic time.
That number just defines the sheer massive scope of that initial in-body calculation. You're modeling every significant lump and bump in matter density across this huge volume of space, simulating gravity's effect over cosmic history.
Think about the memory needed just to store the position and velocity of 4 trillion points at any given moment.
Let alone calculate all the forces between them constantly.
Exactly. It's a staggering computational feat.
And managing that 4 trillion interacting particles in one giant calculation, that's almost beyond imagining. It needed serious computing power, right? Institutional scale. Where did they actually do this?
Yeah, this monster calculation was run back in 2019. They used the PISDAINT supercomputer at the Swiss National Supercomputing Center, CSCS, in Lugano, Switzerland.
PISDAINT, wasn't that one of the fastest in the world at the time?
It was indeed. In 2019, PISDAINT was ranked the 3rd most powerful supercomputer on the planet.
Okay, and to give people context on what that means in terms of resources, the sources really highlight the commitment involved. This wasn't just like a big job they ran overnight.
No, far from it. Get this. More than 80% of PISDAINT's entire capacity was dedicated solely to this one calculation.
80%. Imagine basically shutting down almost everything else happening at a major national supercomputing center just to run one simulation.
It shows you how important this was and just how challenging it was computationally. Stadel himself said, and I'm quoting here, "It was a huge challenge to simulate such a large portion of the universe at this resolution in a single calculation."
Because it had never been done before. They needed that massive, sustained dedication of resources.
Absolutely. It pushed the limits.
So it's important for people listening to understand this two-step process, right? First, the pure physics. Track those 4 trillion particles, let gravity shape the cosmic web over billions of years. That builds the underlying framework.
Yes, the scaffolding, the dark matter distribution, that's step 1. Step 2 was then more astrophysical and arguably more complex in some ways. Once you have those structures, the dark matter halos where galaxies should form, the connecting filaments, you then have to populate them with synthetic galaxies. And these aren't just random points. They have to obey the known physical laws of how galaxies actually form and evolve. And critically, they have to mimic exactly what the Euclid instruments will observe.
So they look like real galaxies to the telescope's cameras and spectrographs.
Exactly. Complete with those 400 properties for each of the 3.4 billion galaxies. This is what produces that realistic blueprint. Stadel talks about a simulation of what Euclid will actually see when it looks at the sky.
So the gravitational physics creates the container, the large-scale structure.
Right.
And then the astrophysics fills that container with the right kinds of objects, the things Euclid's actually looking for, the light sources. That interplay between modeling the invisible dark matter structures and the visible galaxies is really the genius of Flagship 2.
It bridges the gap between fundamental theory and actual observation. Which brings us neatly to the crucial why. Why go to all this trouble? Why dedicate 80% of one of the world's fastest supercomputers to building a fake universe?
And the answer really comes down to the sheer amount of data that the real Euclid mission is generating.
Exactly. Let's quickly ground ourselves in what Euclid is doing.
Yep.
It's an ESA space telescope launched in June 2023, started its survey. And it's designed to look at a huge chunk of the sky, over a third of the entire celestial sphere, with unprecedented resolution, both in imaging and spectroscopy.
That combination of vast area and sharp detail.
Yeah.
That's the source of the problem, isn't it? The data logistics problem.
It is. Julian Atomic, one of the key collaborators on Flagship 2, puts it very clearly. He explains that Euclid produces data in such sheer volume and speed that having humans analyze it manually is just completely impossible.
Give us a sense of that impossibility. You mentioned 3.4 billion galaxies in the simulation.
Right. Now, imagine trying to process the real data for billions of galaxies. Even if, hypothetically, a highly trained astrophysicist could analyze everything about one galaxy in just 1 second.
Which is ridiculously fast.
Totally unrealistic, yeah. But even then, it would take centuries of nonstop work just to get through the catalog once. And Euclid is delivering this data continuously, day after day.
Wow. That's a staggering bottleneck. It almost feels a bit demoralizing scientists build this incredible instrument that produces data they know they can't possibly look at themselves.
Well, it's just the focus. The human element moves away from clicking on individual galaxies.
Right.
Towards designing the algorithms, the automated systems that can handle the load. And this is why the mock data, the Flagship 2 simulation, is absolutely crucial.
Because you need something to test those algorithms on before the real, precious, unique data arrives.
Exactly. You have to develop and rigorously test the methodology for interpreting these massive, complex data sets in advance. You can't afford to wait for the real data stream to start and then begin figuring out how to process it.
You would just fall hopelessly behind.
Hopelessly. You need to be ready to process it almost instantly, often within hours or days of it coming down from the telescope, because the data pipelines have to run continuously to keep up.
So the simulation, Flagship 2, becomes the ultimate training ground. It's the perfect controlled environment for the AI and machine learning algorithms that have to do the heavy lifting.
That's a great way to put it. If the simulation is this perfect theoretical universe based on known physics, scientists can feed that simulated data into their algorithms.
And see if the algorithms correctly identify all 3.4 billion fake galaxies and measure their 400 properties accurately.
Yes. And just as importantly, see if the algorithms correctly identify and handle the errors and complexities they'll encounter in real data.
Like what kind of errors?
Things like instrumental effects, noise, cosmic rays hitting the detector. But also tricky astrophysical things, like accurately measuring the shapes for lensing or dealing with deblending objects. Yeah, where two or more galaxies overlap in the image on the sky, and the software has to figure out that they're separate objects and measure their properties individually. That's really hard.
I can imagine. So if your mock data, Flagship 2, is this perfect high-resolution replica where you know the ground truth, you know exactly where every galaxy is and what its properties should be.
Oh, you know the right answer.
Then you can run your software on it, see where it makes mistakes, and fine-tune it until it reaches the accuracy and reliability needed for the real mission.
Exactly. You calibrate your tools on the simulator before you use them on the real sky.
And this also helps tackle that huge problem in astronomy: systematic errors. When you look at the real universe and find something weird, how do you know if it's genuinely new physics or just some subtle bias in your telescope or your analysis software?
Flagship 2 helps isolate that. If your algorithm processes the perfect synthetic universe and consistently finds, say, that it underestimates the distances to small, faint galaxies, then you know that bias comes from the algorithm itself, or how it interacts with simulated instrument effects, not from some strange new property of the actual universe. You can then fix the code before you let it loose on the real Euclid data.
It really underscores how modern astronomy isn't just about pointing telescopes anymore. It's deeply intertwined with sophisticated data science, computer science, preemptive coding.
Absolutely. The modern astronomer, especially on these big survey projects, is often as much a data pipeline manager and algorithm developer as they are a traditional observer. That simulation isn't a luxury, it's a necessity. It's like a massive digital dress rehearsal or maybe a digital safety net.
Okay, now we get to what, for many people, is the really exciting part: the potential scientific drama. Because while Flagship 2 is fundamentally this incredible technical exercise in preparation,
Data handling, algorithm testing.
its ultimate scientific purpose is actually to challenge our current understanding of the universe, to actively seek out the flaws in our best theories.
It really is a high-stakes test. And it's essential for listeners to remember, as we discussed, that Flagship 2, the mock universe, is built entirely on the foundation of the standard cosmological model.
Which is called lambda CDM, right? Can we just quickly recap what that model actually assumes?
Sure. Lambda CDM basically says the universe is made up of a few key ingredients governed by Einstein's general relativity. There's ordinary matter, like us, stars, gas, but much more importantly, there's cold dark matter CDM.
Invisible, slow-moving stuff.
Exactly. Invisible, doesn't interact with light, moves relatively slowly, and its gravity dictates where structures like galaxies and galaxy clusters form. That's the CDM part.
Okay. And the lambda.
Lambda squared represents the cosmological constant. This is the simplest mathematical form of dark energy, an intrinsic energy of space itself that causes the expansion of the universe to accelerate.
So dark matter pulls things together, dark energy pushes things apart, basically.
In simple terms, yes. And this lambda CDM model, despite its weird ingredients, has been incredibly successful. It explains a vast range of observations, from the cosmic microwave background radiation left over from the Big Bang, right up to the large-scale distribution of galaxies we see today.
So Flagship 2 simulates a perfect lambda CDM universe. And the expectation, as both Stadel and Atomic mention, is that Euclid's actual observations will, broadly speaking, confirm the matter distribution predicted by Flagship 2. That's the baseline hope or expectation.
That's the baseline. But science rarely progresses just by confirming what we already think we know. The real excitement lies in the potential for disagreement. Scientists are actively hoping to find places where the model breaks down.
They explicitly anticipate surprises and unexpected discoveries, as the sources say. They seem quite convinced the model isn't the final word.
Well, yes, because there are already hints, tensions in existing data. Stadel uses that striking phrase. We already see indications of cracks in the standard model.
That sounds significant. What sort of cracks is he likely referring to? Where are these tensions showing up already?
There are a few areas. Probably the most famous is the Hubble tension. Different methods of measuring the current expansion rate of the universe, the Hubble constant, are giving slightly but persistently different answers.
Measuring it locally using supernovae gives one value. Measuring it based on the early universe, light gives another.
Exactly. And they don't quite agree within their error bars. That's a crack.
Yeah.
There are also potential issues, though perhaps less statistically strong, with how dark matter seems to clump on smaller scales compared to lambda CDM predictions, or maybe slight inconsistencies in gravitational lensing measurements.
So these are subtle discrepancies found by cobbling together data from different telescopes, different methods.
Right. And the hope, or expectation, is that Euclid, with its huge, uniform, high-precision survey covering billions of years of cosmic time in one go,
might finally provide data clear enough and statistically powerful enough to show definitively whether these cracks are real, and maybe reveal new phenomena that lambda CDM just cannot explain. Things about the cosmic web structure or galaxy evolution that don't fit the simple rules.
That tension really defines the scientific knife edge here. Atomic sums it up perfectly. It will be exciting to see whether the model holds up against Euclid's high-precision data or whether we uncover signs of new shortcomings.
So Flagship 2 acts as the perfect theoretical benchmark. It's the idealized prediction. Euclid delivers the messy, complicated reality.
And if that reality, the Euclid data, deviates significantly and systematically from the Flagship 2 prediction.
You can't just blame the simulation because you know exactly what physics went into it, standard lambda CDM.
Precisely. The blame has to fall on the input physics. The assumptions of lambda CDM must be wrong, or at least incomplete.
And that deviation, that confirmed crack, that's where the scientific revolution would have to start.
Absolutely. It would force cosmologists back to the drawing board. Do we need a more complex form of dark energy? Does dark matter have some unexpected properties? Does gravity itself behave differently on cosmic scales than Einstein predicted?
Maybe considering alternative theories like MOND, modified Newtonian dynamics, or other modified gravity ideas?
Potentially, yes. The simulation, by providing that precise baseline, clarifies exactly where and by how much the standard model is failing. It points the way for the next generation of theories.
Okay, let's zoom in on one of those potentially revolutionary areas, dark energy. It's arguably the biggest mystery in cosmology. And within that standard lambda CDM model that Flagship 2 is built on, dark energy is represented in the simplest possible way, right?
Exactly. As Stadel puts it quite bluntly, in the model, dark energy is just a constant. It's the cosmological constant, lambda.
Meaning it's unchanging.
Unchanging in space, unchanging in time. It's treated as an intrinsic property of space itself, a constant energy density everywhere that doesn't dilute as the universe expands. It's the simplest mathematical term you can add to Einstein's equations to get accelerated expansion.
But the whole point of Euclid, one of its primary missions, is to rigorously test whether that assumption holds true. Is it really just a constant? Why is finding that out so critical?
Because if it's not a constant, if its strength or density has changed over cosmic history, then it's not just some background property of space-time. It must be something dynamic, something physical that evolves.
Which would completely change our picture of the universe's past and presumably its future fate.
Absolutely. If it's a true constant lambda, the acceleration continues relentlessly, leading eventually to a big freeze or maybe even a big rip where everything gets torn apart. But if dark energy is dynamic, if its strength changes, well, all bets are off. It could fade away, it could strengthen, it could oscillate.
And isn't this where theoretical ideas like quintessence come in?
Yes, exactly. Quintessence is the general name physicists give to hypothetical dynamic forms of dark energy, usually pictured as some kind of slowly evolving scalar field spread throughout space, a bit like the field that might have driven inflation in the very early universe, but operating now.
So finding evidence that lambda isn't constant would be huge. It would mean moving from this simple placeholder to needing a whole new physical theory of this dynamic field.
Precisely. It opens up a whole new realm of fundamental physics.
So how does Euclid actually test this? How can it tell if dark energy was the same strength billions of years ago as it is today?
It comes back to the sheer scale and depth of its survey. Euclid is mapping the positions and distances of billions of galaxies across a huge volume of space, looking back up to 10 billion years in cosmic time.
So it's effectively creating snapshots of the universe at different ages.
That's a good way to think of it. By measuring galaxies at different look-back times, astronomers can reconstruct the history of cosmic expansion.
How do they measure the expansion rate at those past times? Is it just about how clustered the galaxies are?
It's primarily done through measuring distances and redshifts, very precisely. Redshift, as you know, is the stretching of light's wavelength as it travels through the expanding universe.
The farther away something is, the more its light is stretched, the higher its redshift.
Correct. And the relationship between distance and redshift isn't constant. It depends on how fast the universe was expanding at different times in the past. Euclid uses techniques like measuring baryon acoustic oscillations, characteristic patterns in how galaxies cluster as a sort of standard ruler to get precise distances at different redshifts.
Ah, okay. So by measuring these standard rulers at various distances and thus various past times, they can chart the expansion history.
Precisely. Adamic frames the core question they're asking. We can see how the universe expanded at that time, looking back billions of years, and measure whether this constant really remained constant. They're literally mapping the acceleration rate over cosmic time.
And if that acceleration rate was different, say, 5 billion years ago compared to 10 billion years ago, or compared to today,
then lambda is not a constant. Game over for the simplest model. That would be the smoking gun evidence that we need new physics beyond standard lambda CDM to explain dark energy.
Now, Stadel does add a note of caution, right? He suggests Euclid might not deliver the final definitive answer on dark energy overnight.
Yeah, he manages expectations a bit. It's unlikely to be a single eureka moment from one data release. Understanding dark energy is incredibly challenging, but he expresses strong confidence that Euclid will bring us a step closer to understanding the mysterious realm of dark energy.
It's about gathering that unprecedentedly precise data needed to really start ruling out possibilities. Can we rule out the simple constant? If so, what kind of dynamic behavior does the data favor?
Exactly. And again, having Flagship 2, which was built assuming lambda is a constant, provides that perfect reference point. Any deviation Euclid finds in the actual expansion history will stand out starkly when compared to the simulation's prediction. It sharpens the search.
So, to achieve these really ambitious goals, testing the constancy of dark energy, mapping dark matter, looking for cracks in the standard model, Euclid relies on some pretty sophisticated observational techniques. We should probably touch on those. It's not just taking pretty pictures.
Definitely not. It's about precision and scale combined. It really is the most comprehensive survey ever attempted.
Right.
In terms of both the volume covered and the detail captured within that volume.
Okay, let's start with mapping the invisible stuff, dark matter. You mentioned gravitational lensing earlier. How does Euclid actually use that?
Right. So Euclid has incredibly high spatial resolution, meaning it can take really sharp images. This allows its researchers to detect very subtle distortions in the shapes of literally billions of distant background galaxies.
These aren't the dramatic arcs and multiple images you see from strong lensing around massive galaxy clusters.
No, this is weak lensing. The effect is tiny, just a slight statistical preference for galaxies behind a massive structure to appear slightly stretched or sheared in a particular direction.
Like looking through a very subtly warped window pane, as you said.
Exactly. And the warping, the distortion, is caused by the gravitational pull of all the mass lying between us and those background galaxies primarily, the invisible clumps and filaments of dark matter that make up the cosmic web.
So by measuring these tiny, systematic distortions across billions of galaxies spread over the sky,
scientists can essentially reverse engineer a map of where the intervening mass must be. They can figure out the distribution of the stuff doing the bending.
even though they can't see the dark matter directly.
Correct. The result is a massive three-dimensional map of the dark matter distribution across a huge portion of the universe. This map is crucial for testing the predictions of Flagship 2, which, remember, simulated precisely how dark matter should be distributed according to lambda CDM physics.
Okay, so weak lensing gives you the map of the mass distribution, but you need to know where things are in 3D space, especially their distances, to make sense of cosmic evolution and expansion history. How does Euclid get the distances?
That's where the complementary technique comes in, spectroscopy. Euclid has an instrument called NISP, near infrared spectrometer and photometer, that can measure the spectrum of light from millions upon millions of galaxies.
Breaking the light down into its constituent colors, like a prism does.
Exactly. And by doing that, scientists can measure the galaxy's redshift with very high accuracy. They look for characteristic features in the spectrum absorption or emission lines from specific chemical elements and see how much they've been shifted towards longer, redder wavelengths due to cosmic expansion.
And as we established, redshift is the key indicator of distance in an expanding universe. More redshift means farther away and further back in time.
Precisely. So by getting these accurate spectroscopic redshifts for a huge number of galaxies, Euclid can pinpoint their distances with unprecedented accuracy. This is what allows them to slice the universe up into those different time bins we talked about to map the expansion rate over 10 billion years.
So it's the combination of the two techniques that's really powerful. The sharp imaging gives you the galaxy shapes for weak lensing, mapping mass.
And the spectroscopy gives you the precise redshifts for distances, mapping expansion history and 3D position.
That's the synergy. You put them together, and you build up this incredibly detailed three-dimensional map of both the visible galaxies and the invisible dark matter structures, spanning this enormous cosmic sphere with a radius of 10 billion light-years. It's a survey of cosmic structure and evolution, covering more than 2/3 of the universe's entire history.
Just staggering. And there's one more benefit of casting such a wide net, isn't there? The possibility of finding things you weren't even looking for.
Ah, yes, the element of serendipity. Because Euclid is surveying such a truly vast volume of space, the chances of stumbling upon extremely rare or unexpected objects or phenomena are actually quite high.
Adamic mentions this, right? That some things are just intrinsically extremely uncommon, maybe a specific type of superluminous supernova, or a weird kind of quasar, or a particular stage of galaxy merging that only happens fleetingly.
Exactly. In any small patch of sky, you might never see one. But when your survey volume encompasses billions of light years, you're bound to catch some of these rare events just by sheer statistical luck.
That's the idea. Adamic says the chances of finding unexpected or rare objects are high. This is pure discovery space. You might find objects or phenomena that challenge existing theories in ways nobody even anticipated simply because nobody had looked wide enough and deep enough before. #outro. So, to kind of wrap this all up, this incredible Flagship 2 simulation, this universe built inside PISDATE, it's playing these three really critical intertwined roles right now at this pivotal moment in astronomy.
Okay, let's recap them first.
First, it's the essential data preparation engine. It allowed scientists to develop and test the automated software pipelines needed to actually handle Euclid's massive data volume. Without it, they'd be drowning.
Got it. Second,
It's the highest precision testbed ever created for the standard lambda CDM model of cosmology. It's the perfect theoretical prediction against which the real universe will be measured.
looking for those cracks. And third,
Building on that, it serves as the indispensable guide for interpreting the complex cosmic history that Euclid is now observing. By comparing the real data to the simulation, scientists can better understand the growth of structure, the evolution of galaxies, and the nature of dark energy over time.
and this isn't just theoretical anymore, things are happening. You mentioned the first data release, the quick data release that came out in March 2025.
That's right. Even that was just a small taste, relatively speaking, of the full survey. But it already provided new insights, particularly into galaxy clusters and the structure of the nearby cosmic web. And papers based on that and related simulation work are already being published in journals like Astronomy and Astrophysics.
And there's a plan for more data coming soon.
Yes, the next major planned data release, which will be significantly larger, is expected sometime in spring 2026. So the pace is really picking up.
It's a rapid unfolding of discovery where every step relies heavily on that groundwork laid by the simulation. Those processing pipelines tested on Flagship 2, they're running now on the real data.
Absolutely. The preparation is paying off.
What really stands out to me, thinking about the whole project, is the almost philosophical intent behind Flagship 2. Here we have the most sophisticated, detailed digital model of reality ever created, built explicitly, not just to confirm what we think we know, but specifically to find the errors in our understanding. It's like building a perfect machine designed to highlight its own potential flaws when compared to the real thing.
That's a great way to put it. It's a theoretical construct designed, in a sense, to be proven wrong, or at least incomplete, in the most informative way possible.
And that sets up this fascinating tension that you, listening, should really keep in mind as the Euclid results continue to roll in over the next few years.
Exactly. You've got this perfect, pristine, synthetic universe inside Flagship 2, totally controlled, high resolution, built strictly on the rules of lambda CDM physics. And then you have the messy, noisy, complex, real data arriving from the Euclid telescope, full of unexpected glitches, statistical fluctuations, and potentially truly baffling outliers.
So the big question becomes, if the broad strokes match, if the overall map of the cosmos looks roughly like the simulation predicts, but there are these nagging discrepancies, maybe dark matter clumps slightly differently in nearby voids than expected, or maybe a few of those super rare, unpredicted objects keep popping up, which do you trust more?
Do you emphasize the broad confirmation that seems to reinforce decades of established physics? Or do you focus on those unexpected outliers, the cracks, the things that don't fit the model and seem to demand entirely new theories?
That tension right there between the expected pattern and the surprising detail, that's where the future of cosmology is being forged. That's where the discoveries will likely lie.
Absolutely. It's an exciting time to be watching. Thanks for joining us for this exploration.
We'll see you next time.